Okay, thank you very much. It's a great pleasure to be here. I am also, just like Levant was saying, I'm a graduate of the last millennium. I tell my students I'm from last century, so it's true. I was also here from 1986 to 1991. And it's wonderful to be back. I've been back here a couple more times before this, but it's wonderful to be here. So I wanted to talk briefly about a topic that we stumbled upon in the process of doing some other research a few years back. And that's regarding surface plasmon backscattering enhancement from layered rough surfaces. I work quite a bit in my recent research with remote sensing of the Earth, of terrestrial environment. And the reason for that is that characterization of subsurface soil structure and water content is very important in many applications, such as the global water cycle, the carbon cycle you've all heard about, climate change. So people want to know how the water cycle is changing. And so using electromagnetic waves and radar techniques, we have been able to get a lot of information from subsurface structures. And you could also have vegetation on top of the layered subsurface structures of the soil. Vegetation have roots and branching structures. So we deal with very large random media type problems in solving radar scattering problems. And we've had some recent success using VHF and UHF frequencies, and these go from 100 megahertz to 500 megahertz roughly. And the way that works, if you just look at the cartoon that I have here, so if this is just bare earth, bare ground, underneath it you could have multiple layers. So if you dig into the ground, you're going to see different layers of dirt, different water contents as you dig down, different profiles of water content, which changes the permittivity or dielectric constant of the soil. The soil could have various inclusions in it. And if you have an incident electric field, part of it is going to be, well, actually the majority of it is going to be reflected via the Fresnel process. You can have part of it go into the ground, interact with subsurface layers, and it will come back up. Because of this multiple interactions between surfaces and because of the roughness of these surfaces, you're going to get something back in the backscattering direction, in the monostatic direction. And that's the roughness of the ground is really the main reason why you get something back in the backscattering direction. And when we fly radar systems on airborne or spaceborne platforms, that's the mechanism by which we actually receive anything. If you have vegetation, same thing. Okay, so and also there's a bunch of other applications, not just the remote sensing of environment, but also other things like if you are interested in circuit boards, multi-layer boards, and especially if you go to higher frequencies, there's very small scale roughness on there that impact the performance of these boards when you have multiple deposit layers, for example. So basically this is the problem, this is the type of problem we were solving, and then we came upon this interesting phenomenon of surface plasmon waves. But first, before I go to the surface plasmon waves, let me just give you, in the next 4 or 5 slides, I'll just give you a little background on how we solve this layered rough surface problem first. And then from that, I'll go to the surface plasmon waves. So this is the statement of the problem, the very basic geometry of it. So you have multiple rough surfaces. In this case, I've shown you 2 rough surfaces, rough interfaces. In between them, you could have a profile of dielectric constant. It's just like when you water your plant, depending on how deep it is, you get more water or less water, and that defines a profile. So, and then let's say we're probing it with waves at some incidence angle theta I. So the solution to this problem, the backscattering solution, I should say scattering solution to this problem, is what we have been working on is based on a scattering matrix method. Let's just call that SMM. So the way we do it is that we cascade reflection and transmission matrices from different layers. Okay, so which means first we need to find the reflection and transmission matrices for each what I call a system. So if I have 2 rough surfaces, I have 2 systems. The top layer, the bottom layer, each one has a reflection transmission matrix associated with it, and then we cascade those matrices. This is a coherent full wave solution, and in principle, it includes all orders of scattering. So starting from a single rough surface, we can define, so if this is the incidence angle, theta I, we can define scattered waves which go everywhere. So if you want to think about the contrast between this case and a flat surface, the flat surface has one incident wave, one reflected wave, and one transmitted wave. When you have a rough surface, you have an infinite spectrum of reflected waves and transmitted waves. If you want to think about it in discrete waves, in discrete terms, then if these directions are very, very tiny, the separation between them is very tiny, then you could have a spectrum, a discrete spectrum of reflection and transmission matrices. Okay, if you have a stratified medium, now this is a pretty standard problem actually, you can, and if all the layers are flat, then you have reflection and transmission matrices in just the coherent wave directions. Now when you put everything together, so let's say if you have two rough surfaces, some kind of a profile in between, or it doesn't have to be two, it could extend to n layers. The way we define the reflection, the composite reflection operator is through the reflection and transmission operators of individual components of this system. In this expression, again, this is something that for, not for rough surfaces necessarily, but for layer structures, this is a known way of representing the composite reflection operator. But again, we're extending this concept to random rough surfaces. And so once we have the composite matrix, the reflection matrix, then, or rather the composite, this R matrix, we can find the reflected wave due to the entire system. Okay? Now, there's a lot of fine print in here, and because the time is short, I'm summarizing the contents of several papers, basically in almost one chart. So what happens is that once we cascade these different layers, essentially we're defining for the combined system, we define a scattering matrix, an S matrix. And so think of this as an S matrix, and it has, again, a lot of fine print in here, and I have given you very, general expressions for how we get the components of this S matrix. And the way because we're dealing with random rough surfaces or random media, the way we deal with finding the scattering matrix in this case is that we define periodic boundaries. Okay, so we assume each rough surface is very, very large, is long enough that if you put another replicate of itself next to it, they don't really talk to each other. This way, because we have now a periodic surface, we could use discrete Floquet modes to represent the plane wave spectrum of the reflection and transmission processes. And so a lot of the expressions you see here come from the Floquet mode expansion technique. But the bottom line, just the takeaway message from here, is that ultimately we find the scattering matrix, which is a collection of reflection and transmission operators for the entire system. That is a result of cascading individual system reflection transmission operators. And we've done a lot of comparisons with numerical techniques, but I just want to show you how the scattered wave actually looks like. So on the left, we have the HH polarization, and let me see. Actually, both of them are HH polarizations here, but for different surface roughnesses. Okay, so we start from slightly rough surface, and then we go to a little bit larger roughness. So the largest roughness here is 1/10 of a lambda. This one over here, this is 0.03 lambda. And then I've given you the dielectric constants for the two layers, incidence angle, and the separation between the layers. The parameters are completely arbitrary. You could just pick and choose whatever you want. The idea here is this. Let's say the incidence angle 35 degrees. So the wave is coming from basically right here somewhere. Okay, and that shows, because this peak that you see, this is the Fresnel reflected. That's the coherent wave being reflected at 35 degrees. Everything else, if you had a flat surface, no roughness, then everything else would just be, in dB, would be negative infinity. It would be just zero, nothing coming back in any other direction. But now that we have a rough surface, and here's a layered rough surface, then of course we get stuff back in the backscattering direction as well. Okay, and the other methods that you see compared with, we have method of moments and small perturbation method for the small roughness, and here method of moments for the larger roughness. And so the method that we have developed agrees quite well with the numerical techniques. And by the way, when I was talking about the periodic surfaces that we layer right next to each other, we also use the extended boundary condition method in that process, and that's why here, if you see EBCM, that's what it stands for, the extended boundary condition method. Now, so that's the background. This is what we were doing, in studying the layered structures for our remote sensing applications. And then, sometimes, there's something in front of you, and you just tweak it enough, and interesting phenomena come out. So scattering from layered random rough surfaces become really interesting when there's a permittivity reversal. Okay, so now a couple of my colleagues, before me talked about metamaterials. So this is sort of like that. It's not exactly a metamaterial situation here, but when you have a layered surface or a layered structure, you have a dielectric on top of a metal, for example. At high frequencies, metals have negative permittivity. So when there is that permittivity reversal, we notice that we can predict the surface plasmon behaviors, what happens there, using this technique. Now, the surface plasmon waves are not a new thing. I mean, it's not like we discovered that they have been known for a long, long time. But we actually can simulate and predict it with this technique. So the surface plasmon effect exists even with a single surface. Even a single rough surface can produce a surface plasmon wave. And there are different mechanisms for that. You could attribute it to multiple scattering effects. Could be also resonance effects that cause it. When you have a layered, or a set of rough surfaces that have been layered, you can see, as a result of surface plasmon resonance, you see enhanced backscattering. Okay, in the previous charts, this one, for example, the backscattering direction is right here. Okay, there's something, I mean, definitely it's measurable, but there's no special thing going on. You see this trend, downward trend. But when you have the layered rough surface with the permittivity reversal, there's actually an enhancement exactly in the backscattering direction. Okay. And the surface plasmon effects are really interesting. I mean, not just because of their academic interest, it's just a really clever thing that happens, but also it has applications. It turns out the surface plasmon resonance effect, when you have multiple rough surfaces, it's very sensitive to the layer thickness, and it's sensitive to layer thickness well below the diffraction limit. So if you have two surfaces very close to each other, and the separation between them is very small, less than half a wavelength, which is the diffraction limit, you actually pick up that sensitivity to layer thickness, and that then opens up applications such as, for example, people doing biological assays can use that phenomenon when you're trying to grow layers, small, very thin biological layers on top of different structures. You can see in optics and photonic devices, those are of interest as well. Wherever you have a thin layer, if you have a metallic layer, you deposit something on, or you have you put a dielectric layer on top of it, or vice versa. If you have, for example, a dielectric substrate, you deposit metallic layers on top of it. That's where these phenomena can find applications. So let me just talk about how we pick up these things. So as I mentioned, one of the reasons surface plasmon resonances or waves could happen could be a result of multiple scattering processes. Surface plasmons, I mean, the origin of the word, think of it as plasma with negative permittivity below the plasma frequency. Their characteristic is that they decay evanescently away from the surface. So in this picture, if this is the z direction, they're evanescent in the z direction. They propagate along the surface. So the wave number, so there are waves that have some positive k in this direction, in the transverse direction, and then because of various multiple scattering effects, they also get bounced back, so they have a backward traveling wave number component as well. Okay, so and another thing that happens is that when the interface is rough, the evanescent waves can get coupled to propagating waves, and that's another mechanism by which they they can reverse their directions as a propagating wave. So when you have multiple rough surfaces stacked on top of each other, so here I've shown two, multiple surface plasmons can get induced in this structure. So a single surface can do one set of plasmon waves, but multiple structures can, or multiple rough surfaces can have multiple surface plasmon modes that get excited. Okay? So for a moment, let's forget that these surfaces are rough, and let's see if roughly we can predict where these surface plasmons occur. So if you have just flat, planar surfaces, you can easily write the waves in each region, apply the boundary conditions. So we have region 0 up top, region 1, and region 3. Okay, and think of these as just different media with different dielectric constants. And we know that for surface plasmons, if you're after surface plasmons, all the Z component, all the Z propagations are not propagation, actually. These are evanescent waves, so that's why you see K in the X direction, but Z or alpha in the Z direction, saying that these are evanescent waves. So you go through the motion, apply boundary conditions, and you come up with dispersion relations for this two-layer structure. So basically, set of two equations. Here, this set is for TM waves, this is for TE waves. Now, the interesting thing here is that if you have a single surface, surface plasmons can only exist for TM waves, just because the boundary conditions don't allow them to exist for TE waves. But once you stack them, turns out that the TE waves actually also can have surface plasmon modes. Okay, but the bottom line is that you come up with the dispersion relations, and from this you can solve for the alphas here, which would be the alphas corresponding to those surface plasmon modes. Now, these are discrete modes, and if you solve them graphically or numerically, this is an example of what you would get. This is for the TM case, that's for the TE case. On the horizontal axis is the layer thickness, and over here, this is the actual value of the K value for the surface plasmon wave. So here, I'm showing you two of these modes as a function of layer thickness. As for the TM waves, there's always a surface plasmon. You can always find the surface plasmon mode. But as I mentioned, they're discrete, so as you increase the layer thickness, you can fit more and more of these modes. They become weaker and weaker because they depend on the evanescent spectrum. So once the two layers get too far from each other, then even though they in principle exist, but they're very weak. For TE waves, they don't show up until some finite thickness, in this case 0.15 lambda, and then you can also find the second mode. So, these two and these two correspond to the two discrete surface plasmon modes here. But these are for smooth layers, flat layers. When we go to the rough surface, there's no theory that can predict it. I'm just showing you this so that we have a notion, we have an idea of roughly where we can expect the surface plasmons to occur when we go to the rough case. Now, the rough case is what we solve with the method I started with at the beginning of my talk. So we use the scattering matrix method and the extended boundary condition technique to simulate the case for a two-layer rough surface where the top layer is the dielectric, and I think I will show you. I don't know if these. Let me see. Okay, well, I forgot to. I should point it out here. So these modes, which also correspond to the next pages, the top layer has an epsilon of 3. The bottom layer, this would be silver, for example, at very high frequencies, minus 18. So that's where we get the permittivity reversal, and that's what actually enables the surface plasmons to exist. Okay, so for the same case, for the same two values of permittivity, but now with roughness. So now we have H is the RMS value of surface roughness for the two layers. Now you see the different colors correspond to the different separation between the two surfaces. Okay, so the blue, this is the shortest distance between them. The red, let me see, this pink here is half a wavelength. The blue here is 0.3 wavelength. There's no linear trend here because, again, it is a nonlinear phenomenon. It's multiple scattering. It depends on the evanescent spectrum. But there are cases where you actually pick up the backscattering enhancement, which are also called in the Plasmon wave jargon, they're also called the satellite peaks. We pick them up with our scattering matrix method. So for example, let's look at the one, this light blue color here. And if you look at the two arrows, these two little ears or peaks, these are the satellite peaks. These are the result of enhancement due to the Plasmon waves. The theoretical value just for the two smooth surfaces would be, for example, at 38.7 degrees, we get it at 37.6 degrees. The other one would be at minus 53, we get it at minus 52. So our numerical results for the rough surface very closely predict or match what was predicted from just the flat geometry. So this gives us confidence that what we're doing, we're actually picking up this effect. Okay, and that's another example for the half a lambda case. And this is yet another example, the same thing, TM and both TE and the TM wave shown here and the TE also shown here. Okay, now the interesting thing I mentioned earlier was that this phenomenon is sensitive to sub-wavelength features. In fact, below half a wavelength features. Okay, so the green here is TM, the blue is TE, and this is the backscattering coefficient from the two-layered rough surface as a function of thickness or the separation between the two layers. So for the TE, remember that below certain separation in terms of wavelength, there really wasn't a surface plasmon mode that we could find. And that shows here because this is a very weak effect here. It's pretty pronounced at, for example, almost 0.1 lambda for the TM case, it's pretty pronounced. So we see backscattering enhancement here. And you see this periodic behavior as we change the thickness or the separation between the layers. Half a lambda is right here. So you see that even before half a lambda, there's quite a bit of sensitivity of the backscattering coefficient to, and this is the enhanced backscattering coefficient. So this is the result of the surface plasmon resonance. And this is where I was mentioning before that this phenomenon can be used for a lot of interesting application having to do with dielectrics on metals or metals on dielectrics whenever there is that reversal of permittivity. Okay. So with that, I just wanted to say a few things just to wrap up. So there's a lot of basic concepts in this talk that I really learned, 20-some years ago, almost 30 years ago, from Professor Hsieh, whether it was the various classes I took from him or partly my research. Actually, most of what I was just talking about didn't have much to do with my Ph.D. thesis topic at all. But no, I learned it by classes, osmosis, whatever you want to call it, and it's a long list. Scattering for sure. I mean that's the overarching principle here. Evanescent waves, extended boundary conditions, transmission matrices, scattering matrices, layered media, surface plasmon wave, guided waves, pretty much everything about TM. So I learned here from Professor Hsieh, and that's all very valuable. It was a very unique, very fascinating, wonderful education. But the most important thing I learned from Professor Hsieh was how to find complex problems and how to solve them. And that's just priceless. You really can't replace that with anything, and I'm thankful to you for that. So with that, I'll finish.
Thank you for a very interesting talk. Are there any questions for Professor Mahta Moghaddam?
Okay.
Yeah, Laban, you have a question.
Yeah. When we talk about rough surface scattering, we usually think of the Earth surface or the sea surface. But have you come across any applications where this can be used for the roughness of some like nanoscale structure.
That's exactly right. So that's among the other applications I had put up here. That yes, I mean when you deposit metal, for example, on a substrate, yeah, I mean if you look at it, closely, there's roughness, and that's not periodic structure. It's a random roughness, and I'm not sure if there has been too much investigation in that, but it could have interesting implications, yeah.
This work is useful in many different scales.
Absolutely, yes, yes. And actually for, when we go to the regimes of small roughness, it becomes more and more accurate. Okay, whenever you stretch, I mean, just like your problems, when you go to larger and larger problems, you're stretching something. Right. And something gives from, from somewhere. But it becomes actually for small scales more and more accurate.
Thank you.